I believe we're looking at like a swing. So there's two states of the problem that I think are in question. There is when it's pulled back, and they don't give us an angle, they give us the height that it was pulled backwards. So there's that, which is kind of nice. I can't remember on your exam whether they give you the angle or they give you the height that it's pulled back. So, you know, if they give you the height that it's pulled back, yay. If they give you the angle that it's pulled back, you know, then you're going to have to do a little more work. So I think that's why both questions are there, because you should be able to do both. But they gave us that this is 5 centimeters, but they also said that it was given a push of 1 meter per second. Mass of 2 kilograms. Now, I'd like to know how fast it's going to make it to its lowest point here. So conservation of energy is probably the best way to go here. And the fact that they don't ask what I feel is the obvious follow-up question, I will at the end of this ask the follow-up question. But to figure out the velocity at the lowest point, I'm going to use conservation of energy. We have both gravitational and potential. We have gravitational potential and kinetic, right, when it's given the push. And then the lowest point will be the point where there's no gravitational potential and it's all kinetic. So I'm thinking mgh plus 1/2 mv squared would have to equal 1/2 mv squared. Them giving us the 2 kilograms is either a distractor or they plan on using it later, but I don't need it, so I'm gonna get it out of the way. And now I want to figure out how fast it's going, so I have 0.5 plus 0.5 equals 1/2 v squared. So v is going to be the square root of 2 meters per second. I think the likely follow-up question would be, what is the tension in the cable at the lowest point? If I were you, I'd be able to do that question, although I don't know if it's on the exam or not. If I were writing the exam, I would have it on there. The only problem with that is it relies on you getting this answer correct in order to do the next part, because you have to know how fast it's going. The way around that is for them to give you the velocity at the bottom and ask for how high it was at the start, and then ask for the tension in the rope. So it's the same question when it comes to what knowledge you have to find the height if they give you the velocity at the bottom. So to find the tension in a rope, which is not actually in this question, you would say net force equals MAC. Ava, do you want me to move?
No, it's okay.
You sure?
Yep.
Okie doke. Which would be, at this moment, there is tension and weight. So tension minus weight would equal mv squared over r, which now is tension equals 20 plus 2 times 2 over, did they give us the length of the string in the prior question? No, so I guess we can't actually do the question without the length of the string. So the 2 is a true distractor, but that would be how you'd figure out the tension. You'd have to do net force and use centripetal acceleration. Okay. Next. Yes, sir.
You could find the length of it if they gave you the angle, right?
Yeah, you could. And just as a reminder, that's how height and the length are related. You won't be able to use your equation sheets on the test. I'll be giving you fresh equation sheets. So if you're writing on your equation sheet, it's good to have it, but you need to memorize this one, I think. Even if it's not on your test, it's probably on the AP exam. Okay. But it doesn't hurt to be able to be successful at it, to take a look at it. They tell us the building is 10 meters high. Yeah. And they tell us the ball has been launched at 25 meters per second. You're going to need to make one of these little things. If you're like me and need to like keep track of everything, I'm old, so I need to have ways of keeping track of everything. The change in y is 10 meters, so I'm going to make downwards negative. Vy naught is going to be 25 sine 20 degrees. The acceleration is going to be negative 10 meters per second squared. And we want to find out how long it's in the air so that we can use the horizontal velocity, which is 25 cosine 20 degrees, to figure out how far it goes, which will be 25 cosine 20 degrees times whatever we get for the time. So we got to find the time by using a motion equation. That's going to be negative 10 equals 1/2 times negative 10 t squared, bless you, plus I don't know what 25 sine 20 degrees is, but I'm sure one of you figured that out. Apparently not, so I'll go with that. So 8.5 t. I don't think you're going to be able to factor this. I think the only way to do this is through the quadratic formula. So negative 8.5 plus or minus the square root of 8.5 squared minus 4 times a times c, all divided by 2a. Alrighty. I have no idea.
You don't have to keep going.
Are you sure?
Yeah.
You can just type that in your calculator and just
I understand, and you just plug it into it.
Yeah. Did somebody get the times? Yes, ma'am. 2.5 seconds? Okay. I'm sure there were 2 times, but only one of them probably makes sense. The other one's got to be negative. So 2.5 seconds, 2.5 seconds, 2.5 seconds. So the range will be 25 cosine 20 times 2.5 seconds. So it's what, like 60 or 70 meters? What is it? 60 meters? Excellent. There, I have the answer.
Thank you.
No worries. Next, a 50-gram meter stick. This can either be done using net torque, or if you remember what we did in class, center of mass can be used here. To ensure that we understand the center of mass, I left it on here, and I think that we should be able to do it. It's a 50-gram meter stick, which means that at its center, its own center of mass is at the middle, and that's where the 50 grams is. I'm going to make this 0. And they say that we want to hang it at the 30 centimeter mark. So basically what we're saying is we want X center of mass to be 30 centimeters. So we have to place a 100-gram mass somewhere to shift the center of mass. I'm just going to assume that the 100 grams is probably going to be placed like over here someplace. I don't know where it is, but I'm going to say it's over here. And I'm going to just put a value of X here. The center of mass formula says that X center of mass is the sum of Xi times, I should write it correctly. Mi times Xi over the sum of the mass. So in this problem, that's going to be 50 grams at 50 centimeters plus 100 grams at some place, all divided by 150. And this has to equal our center of mass of 30. Any question about any of the decisions I made there? Yes, ma'am.
For the 50 centimeters, did you just put that because that's like the middle of the meter?
Yes. We're going to assume it's at its middle. You guys actually measured it in the lab, but without that, we would have no place to start. So I'm just going to say it's at its middle. And most of you found that it was at the middle, maybe off a few millimeters either way. So 30 times 150 is going to be 4,500. And 50 times 50 is 2,500 plus 100x. So subtract 2,500 from both sides and get 2,000 equals 100x. So x must be 20 centimeters. That must be where we place it in order for us to have a center of mass at 30. Yes, ma'am.
Wait, why do you put 50 and 50 together and not like the 50 and 30? The 50 gram is hung at the 30 centimeters mark.
Okay, the meter stick is going to be hung here. We want it to balance. So we want to hang it at its center of mass.
Oh, so that, okay.
Okay, so we are assuming that the meter stick has a center of gravity at its center and that the 100-gram mass is all concentrated where it's hung. And so we're using that to calculate the center of mass, trying to move the center of mass to the 30 centimeter place. That's why. Yes, ma'am?
So that's what the 50 times 50 represents.
Yeah, 50 is the M and X for the meter stick by itself. Yes, sir?
So you just treat the mass of the whole meter stick as like 1 point at the meter stick center of mass.
Mm-hmm. Yes. Alrighty. Questions about that? Yes, sir? I had, when I take this out, basically I have 30 centimeters equals all of that. So I multiplied both sides by the 150. No worries. You know, second semester, now that I feel you guys have enough math under your belt, my expectation will be for you guys to be able to find the center of mass using the actual center of mass equation. So things like, you know, the meter stick having a center of mass at its middle, you should be able to prove. We're not there yet, but second semester we'll be doing moment of inertia and we will revisit center of mass. In order to answer the question about Pluto, and any question regarding the acceleration of gravity on the surface of a planet, you should remember that our starting point is the idea that, ooh, that's the worst looking planet ever. Wouldn't want to live there. It's all squishy looking. Because this one's so much better. So let's say this is where Jake lives. The concept about acceleration of gravity is that if you were dropped near the surface of a planet, okay, that's Jake. If you were dropped near the surface of a planet, then the net force on you would cause an acceleration due to gravity on that planet, because the only force acting on you would be the gravitational force towards the center of the planet. Everybody understand that statement, because that's kind of where we start. Earlier today, a student asked me, I don't even know where to start this question. Okay, generally, we pick a fundamental rule as a good starting place. Net force, is a good place to start because we're looking for an acceleration. The force that pulls the person down is the force of gravity. So in this case, I would have the mass of Jake times the mass of the planet times g divided by the separation distance between Jake and the planet. If you're close to the surface of the planet, that will merely be the planet's radius. This is the only force acting. So we set that equal to the mass of the object that's accelerating, Jake, times the acceleration. So under these circumstances, the mass of the object is immaterial, and we get a generalized formula for the acceleration of gravity near the surface of any larger object, planet, moon, asteroid, something like that. So this is the formula that we use to calculate it. Now, in order to find the acceleration of gravity on the surface of Pluto, I would need the mass of Pluto and its radius, which that's the first thing you should study when it comes to this. What you don't need is the mass of the objects. They all experience the same acceleration when they're near something that's very much larger than them. That's why I don't need to know the mass of other things on the planet. Perhaps Matt, a friend of Jake's, because their gravitational interaction doesn't change the answer. So I can't go any further because I don't have the mass of Pluto and the radius of Pluto memorized. And I don't think I have to. I think that that's actually probably enough. Wouldn't you agree, Jake? However, this is generally not the way the question is asked on the exam. On the exam, it's usually asked relative to the Earth. Now, I don't know if this exam has this question or not, but it's so frequent that they do it that way. That one's worth exploring because it's solved a little different. Usually what they'll say is, Jake's on a planet that has 3 times the radius, but only half the mass. Okay, so we're talking 3 times the radius of the Earth, and it's 1/2 the mass of the Earth. That's important because we're able to accept that the mass of the Earth times g over the radius of the Earth squared equals 10. Because we accept that, we can make comparisons to the acceleration on other planets by using this as our reference. This year in AP1, I'm teaching this a little different. What I'm telling people to do is to put in what has changed into a formula like this. So if this is our formula to work from, I would put 1/2 times the mass of the Earth times g, all divided by 3 times the radius of the Earth squared. And then endeavor to kind of filter this out from the numbers. So I want to tease out ME, G, and RE squared. So to tease them out, I'll put the 1/2 out front of the MEG. And after I square 3RE, I'll pull the 9 out and be left with RE cubed. I know that everything in here is 10. Yes?
Should be squared.
Should what be squared?
The-
Oh, yeah, probably. Thinking 3 and writing that. So it looks to me like I would have 1/18 times 10, or I don't know, 5/9. 0.56 meters per second squared. Any question about that? I don't, fractions can appear as your answers, but often they'll go to decimal. Really depends. Yes, ma'am?
So for the exam, will they most likely ask you for the acceleration, or will they do like a ratio questions like other questions?
I really don't know. I mean, I do. I can go look it up. It's in my drawer. But, that's pretty unethical for me. So I could peruse it. But, again, ethics. In E&M, I might do that because I trust all those kids. But I have kids in here that make memes about me. Can't trust them. I'm just joking. 5 minutes before the bell rings, I'll make sure we flip through it real quick, and I'll see if there's any surprises. Yes, sir?
For the second part of that question, you should be escape velocity, right?
Yes. And that's not, I'm sure that's on the test. Just in case you guys didn't hear that, you should be prepared to talk about the escape velocity, And the escape velocity makes the assumption that, first potential energy is minus the work, and that's going to be equal to the change in kinetic energy. Since that is negative mass of planet, mass of object, g over r, that's going to be equal to negative the kinetic energy. The idea here is that mass of planet, mass of object, g over r is going to have to equal 1/2 mv squared to get the escape velocity. This mass represents the mass of the object that's attempting to escape, which is typically not the planet. So if we throw that out, we get the root of mass of the planet, g over r. Knowing when it's r and knowing when it's r squared is pretty important. They're both on the equation sheet, but if I was writing the test question, I would definitely have answers in there for both r and r squared, just because you're probably in a hurry. Yep,
There should be a 2 if you're numerator, right?
Yeah.
sure.
But why is the mass of the planet not mass of the object?
Well, what's trying to escape?
The object.
Yeah, so in the kinetic energy equation, it's not the planet with the kinetic energy, it's the object. Although the planet might try to escape you. It's really hard to accelerate it, though. It takes a lot of energy. Yeah.
So it's only r and the escape velocity, but for the one we just did, it's r squared.
It's r for energy. It's r squared for force. So anytime you're dealing with something with energy, it's just r. And anytime you're dealing with force, it's r squared. So orbits, I say that knowing that orbit, circular orbit, that's not exactly true. Because if you have a circular orbit, it's also related to r. But we start this formula thinking of force. The r cancels because of the centripetal motion formula. Oh well.
Wait, so 13.3 is what happens if the same force is applied to one box?
Well, they're asking about the force on the other box. So you're pushing 20 newtons on one box. The normal force between them is going to be that 13.3 on the bigger box or 20.3 on the other box. But yeah. All right, questions that, use this idea. So I would definitely be familiar with Atwood machine questions because they're very similar and they have all the same kinds of things.
Is this another question? Oh, no.
So any of these. Clear. Based on the way that question is, let's just draw one of them for a moment. So I have some object, and it is forced to go in a circle. Of radii, r? It's a big stretch there. Oops. Is that the center? Close enough? There we go. All right, so this is object of mass m, forced to go in a radius of r, v. All right, so whether it's m or 2m, the acceleration doesn't have anything to do with the mass here. It's v squared over r. So the ratio of m to 2m, ratio for the acceleration of m to the ratio of the acceleration of 2m is 1. They have the same acceleration, so the ratio's got to be 1. Moving on to the next question. If instead they move so that they have the same kinetic energy, what would be the ratio of their velocities? Okay, so they're no longer traveling in a circle. They spent all that time drawing the circle just for that one little thing. Okay, so now they have the same kinetic energies. So I don't know, I'll just get all this out of the way. Bye, get out of there, don't need you. Oh wait, I could use that object. So they both have the same kinetic energy, and I want to know what the ratio of their velocities is. So this one is 2m, this one is m. Here's how I would do this if I were you. We don't know what their velocities are, but k of 2m would be 1/2 times 2m times v2 squared. And k of 1m is going to be 1/2 m v1 squared. Yes? Oh, okay. You understand that really doesn't change very much, but it'll make you feel better because you'll get the exact number. So we want V1 to V3. I'm just going to set these two things equal to each other because they have the same kinetic energy. So 1/2 m V1 squared equals 1/2 3m V3 squared. Cancel the halves, cancel the m, and I'll have V1 squared to V3 squared equals 3 to 1. So the answer of V1 to V3 is square root of 3. I mean, technically, square root of 3 to 1. But that's the ratio. Yay. Next. Now, the circle one, just so you know, the force required to go in the circle would depend on the mass, because force takes inertia into account, but the acceleration doesn't. And this time I'll record it, perhaps. Not that it matters. Recording these things is kind of hilarious. YouTube has changed the rules. I have to select when I submit whether these are actually for children or not.
Oh my God.
And I'm trying to decide, well, you're technically minors. Do I put down? I mean, I don't want to get in trouble with the Google police. But then I realized that, I don't know if you know anything about YouTube statistics. There's like 27 years of footage submitted every day.
Are you serious?
It's something really bizarrely huge. Yeah, so there's a lot of videos being watched every day and a lot being submitted every day. They finally figure out, my little corner. I'm not even trying to make any money, which is good because these videos are so terribly bad. Of course, every time I say that, I realize it's basically exactly what I do in the classroom. So what I do in the classroom is just terribly bad. But you all knew that coming in, that what I do in the classroom is terribly bad. So let me get this right. Help me out here. Nick, is it 2m to m? I'm asking Nick because he corrected me last time. Nick, is it 2m to m this time?
10.
That's what I thought. All right. So yeah, it's 2m to m. And we put a 20 Newton force on one side. Now, we're going to switch sides in a minute. But is the acceleration any different if I push from the left or if I push from the right? Now, net force is 20 newtons. So on the system, net force equals 3m times a. So that's going to be 20 over 3m is the acceleration of the system. Doesn't matter whether I push it from the right or push it from the left. That's not what we're after. But since both blocks have to have the same acceleration, that helps us get to the next point, which is block M is experiencing a single net force in the x direction, which is a normal force. And that normal force is what is pushing block M to the right. Do I need to explain that any more than I just said, or am I okay? So that is the only force causing the acceleration. And that has to be equal to the acceleration times the mass, which is going to be ma, where a is 20 over 3m. So how big is the force acting on that mass? Looks like it's going to be 20 thirds, or 6.7 newtons. Questions about that? All right, well, if instead, I guess I have to leave it like this. If instead I'm going to be pushing on the other side, then all that's really happening is this 20 newtons is now going to be pushing this way. Well, everything else will remain the same, meaning the acceleration of the system is still going to be 20 over 3m because it's the same sized system. But now there's a normal force acting here in this direction. I think this normal force is going to be bigger. Why? It has to push a bigger mass. So it's going to get more of that 20 Newton force. I don't know if you guys have seen this, but basically what's happening is that 20 Newton force is getting split up, and a little bit of it is applying to each of the objects in a row. I bet that this box is going to get the remaining 20 newtons. So if in the first case only 6.7 newtons made it over there, I bet this time 13.3 newtons is going to make it over there. The balance of the total 20 newtons. But let's just see. Net force is going to equal N, which is going to equal 2m times A, which is 20 over 3m. M's will cancel out. This will give me that the normal force is going to be 40 thirds, which last time I checked is 13.3 newtons. So, yeah, I mean, if you don't want to crush the little box, you don't push on it first. You push on the big box and let the big box push the little box. But if you push the little box, you might crush it. I mean, the truth is, the little box is actually having to endure two forces. 20 newtons this way, and 40 thirds newtons this way. Right? That's what that box has to endure. If it doesn't, the box collapses. Bad for the things inside. They could be your Christmas presents, if you celebrate that sort of thing. Could be your Hanukkah presents, if you celebrate that kind of thing. Could be your solstice presents. Or it could just be a birthday present. Maybe you're born around now. Who knows? Yay. So this green line will be the reference line. It seems that the object is on the end of a string and will reach its lowest point here. It's going to be pulled back some angle. They don't tell us the angle, but there is some other information given. They tell me it's 2 kilograms, and that is pulled so that it is 5 centimeters above the ground. And it's given a push, so it has a starting velocity of 1 meter per second. And we're supposed to figure out how fast it's going at its lowest point. Any question about the setup of this question? Conservation of energy seems to be the best way to go with this. Now, in doing conservation of energy, the prior question gave you things like length, theta. It could have also been done as a conservation of energy question. The only difference is that H is being calculated a different way. In this case, H was given to you directly. So I know that I have gravitational potential and kinetic here. You have both because the object was given a velocity instantaneously of 1 meter per second at the start while it's 5 centimeters above the ground. And we're going to be looking at the kinetic energy it has at its lowest point. There'll be no gravitational potential energy here. These have to be equal. So, mgh plus 1/2 mv squared has to equal 1/2 mv squared. The mass was superfluous. We didn't actually need it. So we can get rid of the mass. I had to convert the height into meters because g is in meters per second squared. So g times 0.05 is going to be 0.5 plus 1/2 times 1 squared is 0.5. That equals 1/2 v squared. So v must be the root of 2 meters per second. What they did not ask, which I would have anticipated them asking, is what is the tension in the cable at the lowest point? To me, that seems a good follow-up question. They don't ask it, and there's a couple reasons we can't get the answer. The first is we don't know the length. Without the length, we'd be unable to find the answer. And the prior question didn't give us the length either. But actually, that's probably the only thing keeping us from getting the answer, because net force equals MAC. At the very bottom, that would be tension upwards minus mg downwards. And would have to equal mv squared over L, and we just found V. They gave us the mass of 2, which means we could get an answer. That would be appropriate, in this case. But without a value for L, we can't actually get a number for our answer. Square root of 2 squared, Tyler.
Yeah, but you did t equals 2.
Oh, that should be plus. Thank you, Tyler.
Good job, Tyler.
You're the best. Where's your pencil? Oh, that's right. If I have any projectile, it doesn't really matter what happens to get it to be a projectile. The projectile is going to have our classic parabolic shaped trajectory. Now, let's just handle a couple of what I feel are, obvious things that you had better know. For example, if I label this A, B, C, and D. Here are some things I would want you to be able to tell me. Like, for example, where's the acceleration the greatest? Which, of course, is a trick question. The knowledge that the acceleration is the same everywhere. But by saying it's a trick question belies the fact that you guys will get it wrong. There's bound to be a question on the test that has something where you're supposed to pick the arrow that represents the direction of the net force on the object at point B or point C, and invariably people will screw that up and not put the down arrow. But trust me when I say people don't get this one at 100%. It should be clear that the object never has a velocity of 0. That should be clear, but it doesn't always seem to be clear. People will think that it has a velocity of 0 at B. For the same reason, they think that the acceleration is 0 at B, and neither one of those are true. The object does have its smallest velocity at B, but does not have its smallest kinetic energy at A. It has its smallest kinetic energy also at B, but the kinetic energy isn't 0 there. So you can't set the kinetic energy to 0 at B. It has a horizontal velocity, suggesting that there is a part of its kinetic energy that never changes. You could break the kinetic energy into kinetic energy in the x direction and kinetic energy in the y direction. I don't know why you would do that, but you could. But it is probably appropriate that you recognize that for any projectile, there is a horizontal velocity that remains unchanged during the course of the object's motion. At the same time, there is a vertical velocity that is changing all of the while. So the y velocity is always changing. So way number 1 to figure out the angle that it hits the ground is to find the y velocity and the x velocity. Probably using this angle and the launch velocity to get the x velocity. And then using the launch velocity and the angle to get the initial y velocity and kinematics to get the final y velocity. Once you get those, you can probably use that to figure out the angle that it hits the ground. Tangent would probably be the way to go. And that tangent of theta would equal Vy divided by Vx. Not the only way to do this problem, by the way, because I know that when it's launched, it has both kinetic energy and gravitational potential energy. And when it strikes the ground, it has only kinetic energy. I could use conservation of energy to get the final velocity when it strikes the ground. I could use vectors to figure out the horizontal velocity when it left the ground. And therefore, I would have the final velocity and the horizontal velocity when it strikes the ground. And based on cosine of theta, that would be Vx over V. That's another method to figure out the angle. Both of these methods are valid. I don't believe either one of these gives you an advantage over the other. Except, if you're going to have to do the projectile part anyways, don't do the energy. Do the kinematics. Like if they're going to need the range and then the angle, do the kinematics. Otherwise, it's a lot more work to do the energy, then go back and have to do the whole problem for the range. There's no way to do the range without finding the time. No way. I mean, not unless you solve the trajectory equation, and that's really a lot of extra work. So, is that right? Yeah. Okay, so it's a 30-degree angle. It's slightly downwards. The box is 20 kilograms. And you're to draw a free body diagram. Well, you're not going to be drawing any free body diagrams on the test. But you might have to recognize a correct free body diagram. That's the only way they would test that. So the corrected free body diagram would probably have, the weight's 200, so I should draw that arrow different. There, now they're more appropriately to scale, but that means the normal force arrow is going to be off the page based on scale. And is there friction? Later. Okay. So right now that would be it. If I had to draw in friction, friction would have to be this way. Assuming the box slides to the right or the unbalanced force to the right, friction would be to the left. So let's go on with the questions. Calculate the acceleration of the box if the ground is frictionless. If the ground is frictionless, and that means this equals 0, the only force that's causing this box to accelerate is the component of the force in the direction of motion, which would mean the net force in the x direction would be equal to ma. That's going to be 100 cosine 30 degrees equals 20 times a. Cosine of 30 degrees is 0.886 or 0.866. Times 100 is 86.6. Divided by 20 is 4.3. All righty. So the acceleration is 4.3 meters per second squared. This is question B. Question C, calculate the speed of the box if it was pushed from rest a distance of 10 meters. Well, I could say V naught equals 0. V final is unknown, and delta x is 10 meters, and use a motion equation. Since I've already got the acceleration, that's probably the fastest way to get the answer. But I also remember the work-energy theorem. And if this was the only question on the test, didn't ask all that prior stuff, this would be a lot faster. Because this would just be 100 times 10 times the cosine of 30 degrees for the work. And that would have to equal the change in kinetic energy. The answer will be the same, but if they didn't ask all that prior stuff about drawing a free body diagram and everything, this would lead to the answer much faster. Multiple choice tests don't often have multiple parts. So if I combine these things together here, it's probably because there is a work energy question somewhere on the test, and there's probably a kinematics question or a Newton's law question somewhere on the test. The test is 49 questions, not 20. Moving on, how much work was done on the box? Describe 2 ways you could calculate this value from what you know by part C. Well, I think I've just covered this, haven't I? So by part C, you could get the final velocity and then calculate the kinetic energy. Or it's 100 times 10 times the cosine of 30 degrees, so it's 866 joules. Moving on. Question E. Wow, Mr. Shelton, really? Really? Question E. If instead the box moved at constant velocity due to friction, how much work was done by friction in the 10 meters? Negative 866 joules of energy. Net work would be 0. And since the applied force does positive 866 joules and there's no change in kinetic energy, friction had to do negative 866 joules of work. Do I need to go into that in any more depth? So that's the answer, but it's from the fact that we know the positive amount of work done and that the change in kinetic energy was 0. So again, I'm using the work energy theorem, but setting it equal to 0. And F, what must the coefficient of friction be? There's a variety of ways we could go about doing this. To be honest with you, there's no advantage or disadvantage to going back to net force and finding it this way. Friction is mu times the normal force. And in this problem, the normal force is a little bit complicated. It is 200 plus 100 sine 30 degrees. I have 2 contributions to the normal force because there's 3 forces in the y direction. Are there any questions about that? Do you need me to draw more than this, do a net force in the y direction thing? I would do it if you asked. In the y direction, I see this component of the force, which is 100 sine 30. I have this already there, 200, and then there's normal force, and they have to sum to be equal to 0. So net force in the y direction equals 0, and that's going to be normal minus 200 minus 100 sine 30. That okay? 100 sine 30 is 50, so that means my normal force is 250 newtons. So friction has got to be 250 times mu. Now the frictional force comes from knowing that the net force in the x direction is not ma, but it's actually 0 because we're moving at a constant velocity. So 100 cosine 30 minus friction equals 0. Tells me that the frictional force is actually 100 cosine 30 degrees, or 86.6 newtons. So now, that's how I'd get mu. Something around 0.4.
0.35.
Okay. Now, just to be clear, I see 3 different questions here. They're combined in one, but I bet there's a problem where the net force is 0 and you have to figure out mu. I bet there's a problem that has work being done on a box that's experiencing an applied force, and I bet there's something about kinematics on the test.